That's awkward.
Oh, yeah, showing up now. All righty. Looks like a few of you have shown up. How's everyone doing today? Staying out of the hot weather, although tomorrow is going to be worse. All righty. 20 of you are here. It's probably enough to start, I would think. You all fit on one screen. That's pretty cool. So, any questions from the homework? Negative, huh? You're all kind of done with this Zoom thing, ready to be?
Actually, yeah, I have a question on the homework.
All right. What's your question?
It was back in, let me pull it up. It's an early homework. I kind of skipped it over because I kind of gave up on it.
Okay.
I think it was homework 19.
Do you want to share it again?
Okay.
All right, let me.
You're gonna make kind of like the amount of attempts I've taken. I think it was like 13 attempts.
Let me make you a co-host. All right. You're the co-host now.
There you go. This one.
Okay.
I could not, because you have to get it exactly, so I couldn't figure out which one's which.
All right. The problem is that I am not on full screen, so I can't see your whole. Let me see here. Yeah, can you make it bigger? All right. Oh, there you go. Perfect. All right. So what's the question?
I don't understand which one's which. Like they all kind of look the same, so I was trying to figure out.
Oh, answer, chemical or physical?
Yeah. I have 14 attempts on this one now.
All right, let's see here. Answer. Oh, I think you have to answer each one of these little boxes, right?
Yes, so like it's part of like.
I gotcha. Totally get you. All right. So from here to here, you can see from the first circle down, you can see that the atoms are connecting with different atoms. So that's a chemical change.
Oh, I was correct. Okay.
So if we go from the second circle down to the bottom circle, that's also a chemical change because you're rearranging atoms.
Rearrange. Okay.
Yep. See, so you have a red and a blue in the second circle, and you have a red and two blues in the third circle down. So that's also a chemical change. Going from the middle across, what you're doing is you're separating the double blue dots from the blue-red. Yep, that's physical. From the top half to the right, you're separating atoms which are bounded. So you're separating a compound, a molecule, individual atoms. That's chemical.
Oh.
And then in
And
the
this is
bottom
just,
one, physical. Yep, you're just changing the state.
well, yeah.
Hey! Woo-hoo!
Thank you.
No worries.
That was it.
Any
Yeah,
other
Professor.
ones?
Yeah, I got a quick question for you.
All right, who are we talking to?
This is Marlo.
Hi, Marlo. Did you need to share your screen, or is it just something you can ask?
I'm going to share my screen with you. Sorry, it's because I have a screen connected to different monitors, so I'm going to make sure that it pops up.
All right, I'm going to make you a co-host so you can share your screen.
Okay, there we go. Actually, one sec. Actually, just give me a second because it's on my iPad. 1 second.
No worries. We got time.
Okay, this should work. Actually, can you give my other
Well, I made you the co-host, so you should be able to share anything you've got, right?
second, shouldn't be feeding back. I usually do this on a different computer with my other classes.
You would have to like share your desktop. I think that's what it is.
No, it's not my notes because I'm doing it on my iPad. But I mean, I just want to make sure that the audio is turned off on the iPad before it starts to feedback like that. But there's another. So there's another Marlo in your inside this meet. So if you get access to the other one, then I could share the screen.
Okay, let me see the other Marlo. Oh, you want the second one? All right, no worries. Make co-host. Now the other one is the co-host.
Okay, there we go.
Man, smarty pantses. Woo,
right.
doggy.
So for this,
yep,
I've noticed. So I was working on this problem, and I noticed that for beryllium.
Mm-hmm.
So this can never be actually.
Well, remember, there's exceptions. Yep, it cannot be that guy. We're going to talk about that today. The reason it can't be the second one, like carbon dioxide, is beryllium. Beryllium is too small to form multiple bonds.
So it wants to go either forward or back to the noble gas, correct?
Yeah, right. But in the case of beryllium is happy having 4 valence electrons. He doesn't have to have 8. So remember, hydrogen's happy with 2.
Yes.
Beryllium's happy with 4, and boron is sometimes happy with 6. Right? Those small guys, those first few small guys, they violate all the rules.
And that's only because it wants to go back to, right? So that's only leaves you limited to 4.
Right, okay. Exactly. But it's also because it can't do the second thing like carbon dioxide, because in order for that to happen, carbon dioxide is sharing multiple regions of electron density, sharing S density and P density, and beryllium is too small to do that.
So you're talking about why it can't be this instead of this?
Well, I'm talking either one of those. Beryllium doesn't do either one of those just because it's too small.
Oh, okay, yeah, I definitely understand that, but for
carbon dioxide, for carbon dioxide,
why can't I have 2 electrons notated like this instead of it being...
Why can't it? Because I think when you do that, you run out of You have too many electrons. So if you count the number of electrons that would be possible to put in the picture for carbon dioxide, each oxygen contributes 6, right? Because it's in group 6. So that's 12. The carbon contributes 4, so that's 16 total electrons. If you count the electrons in that bottom picture, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, you have 20 electrons in that bottom picture. You have too many.
Okay, that makes sense now.
Yeah, so
yeah, that's so easy to see now. Okay, never mind.
Well, no, it's great. I'm glad you're asking those questions. We're going to go through a little more of that complexity today, but that's cool that you're working those problems because that's when you run into the questions that, I mean, electron dot structures are easy until you get to the ones that break the rules, like the ASF5, right? It's got 5 things, so it has 10 valence electrons on the central atom.
Yeah, I don't know why I didn't see it like that. I just figured like, hey, there's 2 here and 2 here. Why not just keep them here?
Yeah.
Okay, that just throws it off completely.
Mm-hmm.
Like,
Well, the total electrons, somehow you got those extra electrons in there. You just like gave everybody 8 and you're like, oh, look, I gave everybody 8. But the problem is, yeah, and I see that happen a lot when students do dot structures and they just try to give everybody 8 without keeping track of the electrons. That happens, right? If you said, okay, I got to make everybody join by a bond, then I got to give all the peripheral atoms 8, but I have to keep track of the number of electrons. So if you did that top drawing, or even the bottom one, you would have connected the carbons and the oxygens. That would have taken care of 4. You still had 16 electrons. You could have put 2, 4, 6, 8, 10, 12 on the peripheral oxygen atoms, right? And that would have gotten you, let me think about that. What did we say we had? We had carbon had 6 and 6 is 12 and 4 is 16. You had 16. That would have been all your electrons. You would have been done. And you were like, you scratch your head and say, wait a minute, I'm done with electrons. And then the next step, which we didn't get to last time, is when you run out of electrons, but not everybody's happy, you have to make more.
Oh, okay, I see now.
Yeah.
So this doesn't satisfy oxygen.
No.
Because even if I have them here.
Yep.
Okay, I see what it is.
Yeah. So when you put them in a multiple bond, you get to share them with both atoms, and then it's double dipping, but it's the reality of what's happening.
Okay, sounds good. Thank you.
All right. Other questions? All right. I guess not. Anyone else have questions? Looks like 30 of you are here, so we lost a few people. We're supposed to have 43 and 42. I think somebody withdrew, so we should have 42. No one else? Any other questions? No other questions. All righty then. What I will do is I will share my screen. And you don't care about updates. You don't care about this. You don't care about that. You don't care about this. All right. So what I did, I sent you the link for last class. I also put a couple of other electron configuration practice up there if you want to practice more of those. They're, again, not required. Electron configurations are easy. I think you're really going to have to spend more time on the dot structures, and so we'll spend some more time on that today. We haven't finished the dot structures, so that's why I want to go to this PowerPoint. But what I'm going to do is I'm going to send it to my iPad. Okay, where did that go? All right, so let me share this with my iPad. Okay, so let me stop the share. And let me go back to, okay, that didn't go. Give me a sec here. For some reason, it did not go to my, Let me see if it actually went there. Well, that was odd. It says it sent it to my iPad, but it's not. For some reason it's not opening it in Keynote like it did the other day, so that's annoying. I'll try this one more time. Huh. Why is that not working? Maybe I just close everything and try it again. All right, let me try this one more time. Oh, that's why. Never mind. I'm picking the wrong thing. I'm picking the wrong thing. Notability. There we go. It helps if you pick the right app. Weird. All right. So minimize this. All right. 31 of you are here. All right. So let's go. Lewis structures beyond the octet. So this is all just to refresh your memory. I think you probably got this. You can use either a dot or you can use a dash. By the way, if you're doing a dot structure for like water, let's say as an example, if you do this, oops, sorry about that. If you do this, that's the same as this. So I don't have an issue with you putting two dots, and I don't care if they're horizontal or vertical. It doesn't make any difference to me. Typically, though, we pretty much exclusively use the dash for a bonded pair of electrons. So if you want to consistently look like everyone else in the science world, you would use the dash when the electrons are bonded pairs. Okay, so we talked about the guidelines. I'm not gonna worry about that much, except to just to highlight a couple of things. Central atom more electropositive usually. All right. Sometimes hydrogen is the more electropositive, but just remember hydrogen, as far as you're concerned, is never a central atom. That's only somewhat true. Hydrogen can be a central atom. It's just not going to be a central atom in Gen Chem. And then ligands are just the peripheral atoms. You always connect them with an electron pair with a single dash, a single bond, and then you work your way from there. This is important. Put electron pairs around to form octets. Well, except in the case of hydrogen, right? Because hydrogen only wants 2 electrons. But when you have electrons, you give the outer ones their octet first before you do anything to the central atom. And then at the end, you assign any remaining electrons to the central atoms. And this thing here, beginning with the most electronegative, sometimes you have more than one central atom. I'm going to try to stay away from really tricky ones that have multiple central atoms just because this is Chem 115. This is not Chem 120A. All right. And this is also something to keep in mind. If the central atom, if the atom exists beyond the second energy level, so think about the periodic table. So this is the first energy level, this is second energy level. Anything that exists in the third energy level and beyond, which is pretty much half the periodic, well, more than half of the periodic table, they have access to d orbitals. Remember, d orbitals begin in the third energy level. And that means you can potentially cram more than 8 electrons into those. And we'll talk about those exceptions today. So watch out for those. Okay, then we want to optimize the configuration. We didn't do a whole lot about this optimizing. yesterday or last time we met, just because we were doing simple ones. We'll have more time to do that today. We'll also talk about formal charge, and we'll talk about this thing called resonance, equivalent structures, and things that you can potentially do. Let me just close my email so it doesn't keep dinging on all the time. All right. Okay. Something's weird here. I don't know where my screen share went, so I'm going to stop it and start it again. It was probably there all along, but I couldn't find it. All right, there we are. Okay. So you have this and this concept here called formal charge. A better way of thinking about this is not, the word formal is kind of like formality. It's not really a charge, right? I prefer to call it like a parent charge. And here's a formula. And this formula is just that. It's something that you would store away. It's something you would mechanistically go through all the time. And frankly, I don't like that, even though I'm going to give it to you. I would much rather talk about what does formal charge mean and how can you think about it and how can you make use of it to think about dot structures. Okay, so let's go ahead. I'm going to make a new note and we're going to talk about some specific dot structures. So let me go back here and let me just create a new note. All right. So let's pick a dot structure. So let's pick NO2, nitrogen dioxide. Okay, so let's say I asked you to draw the dot structure for nitrogen dioxide. You would look at that and you'd say, okay, I can do this. I know how to do that. I look at each atom and I count the number of valence electrons I have. So nitrogen's in group 5, so it has 5 valence electrons. Oxygen is in group 6, so I have 6 times 2. There's no charge on this anywhere. It's not NO2 minus, it's the NO2 ion. So this is 5 plus 12. I have, I have 17 electrons, all right? This is an example of something that's going to cause you a little bit of grief. This is an odd number. So let's actually make it the nitrite ion. That'll make life a little bit easier. And then plus 1 because it's a charge. And so this has 18 electrons. It'll make this question somewhat simpler. Okay, so if we're going to look at this and you want to draw a dot structure, that's what you would do. You would count the number of electrons. You'd say, okay, in order to make my picture, I've got to take care of 18 electrons. So I also then have to pick the more electropositive element and make it the central atom. So you got 2 atoms to pick from. You can either make nitrogen the central or oxygen. Generally speaking, the first atom is the central atom. It's not always true, but it's a good guideline. If you forget and pick the first one, that's okay. But also think about periodic table placement. Nitrogen is to the left of oxygen, so it is more metallic. So nitrogen should be the central atom. So I'm going to put nitrogen there. And then even though this says O2 and you might think the oxygens are stuck together, the rules pretty much say just connect those other guys to the central atom, right? So that's what you should do. There might be a temptation to do this, right? Because this is O2. Aren't those oxygens stuck together? They are. And we'll talk about that, why this one here is probably not the right answer, okay? So we'll come back to that. So following the rules, what you would do is you would connect them. And again, I used a dash because they're bonded, so I want to use a dash to represent bonding electrons. So I've taken care of 2 4 electrons. So 18 minus 4 is 14, divided by 2 is 7 pairs, all right? That's how I always do dot structures. And you should design or develop a technique where you are consistently following through and doing the same thing every time. Well, I should be careful. Doing the same correct thing every single time, right? If you do it and you keep getting wrong answers, don't keep doing that. But this is how I always do dot structures, right? So I count the number of electrons. I pick the central atom. I connect the peripheral atoms with a single dash. I subtract however many electrons I used. And again, remember, this is 2 electrons and this is 2, so that's why I subtracted 4. Then I divide by 2 to get the number of pairs. And why do I get pairs? Because now I'm going to use pairs of electrons to make everybody happy. So I have 7 pairs. So here's how I do it. And this is how you should do it. You need to distribute them on the peripheral atoms. So I don't care where you start. 1 pair, 2 pair, 3 pair, 4 pair, 5 pair, 6 pair. So I've used up 6 pairs, right? Minus 6 pairs means I've got 1 pair left, right? But before I do any of that, why did I stop here? Well, this oxygen's now got 8 electrons around it, and this oxygen has 8 electrons around it. So they're happy. I don't need to do any more with those oxygens. I have 1 pair left, and the next rule said whenever you have any more electrons left, you have to put them on the central atom, all right? So you put those electrons on the central atom. That's it. That's where you have to stop. You can't throw any more electrons in there, all right? I know what you want to do. You just want to put 2 more electrons in there and make the nitrogen happy, but where did these come from? I just made that up. No, you can't do that. Even though there's a temptation for you to do that, if you did, you just made NO2 minus 3 because you threw another couple electrons in there, so you can't do that. So the rules say, once you're to that point, the way to make that work is now you have to start shifting pairs that are already bonded in order to make a multiple bond, right? And this lets us talk about a couple of things, all right? First of all, where do I pick electrons from to make them be shared with multiple things? Well, these oxygens both have 8. They don't want any more electrons. So if I were to take this pair and move it there to get this structure, this oxygen is happy. He's got 8, right? The nitrogen, he's not happy. He still only has 6 electrons, right? He had 6 up at the top here. Now he's still got 6. And this oxygen now has 2, 4, 6, 8, 10. That was the wrong move to make. You don't want to do that, all right? So that's a bad idea. So the only other option is to take one of the oxygen electrons, and it doesn't matter which one you take. You can take that one and move it there. You can take this one on the left and move it. It absolutely doesn't make any difference what you do. But if I move that one, then I end up with this picture. O, N, that dot is still there. Now I've got a double bond. And because I moved this, I'm just going to shift these guys to make it look symmetrical, right? That's typically what we do. I haven't changed the number of electrons, right? I'm supposed to have 18 electrons. Let's just double check. 2, 4, 6, 8, 10, 12, 14, 16, 18. I still have 18 electrons, so I didn't change that. Now let me put my circles around the atoms and count. There's 8 electrons in that circle. There's 8 electrons in that circle, and there's 8 electrons in that circle. So this is a valid dot structure for the NO2 minus 1, all right? By the way, I could have just as easily taken these electrons and moved them in there, and if you'd done that, you'd end up with the mirror image of this picture. You'd end up with O, double bond, N, lone pair. Same exact picture, all right? These guys are called, let me pick a color that might show up. They're called resonance hybrids, right? It's the same structure with the multiple bonds in different locations. And you might say, aren't these exactly the same thing? And I would argue, sort of, right? Because I could just flip this picture over and it would look just like that. The reason I'm going to tell you that they're not the same thing is because in real life, neither one of those is the correct picture. The real picture, what resonance is really implying is that this is the real picture. That the bond is something between this structure 1 and this structure 2. But because we're drawing on paper and we're drawing fixed structures, we don't really have a way to show that this electron density is really moving in both of those locations, right? That's really what's implied by a structure. We're trying to draw a complicated picture with simple drawings. And so when you encounter this situation where you have the choice, oh, I could put the double bond here, or I could put the double bond there, you've entered the world of resonance, and you have to show me all of them. In this particular case, there were only 2 resonance hybrids, right? They're equivalent in energy, right? But you have to show them all to me. Sometimes there's 3, sometimes there's 2, right? You have to show all of them when you're doing a structure, okay? What's really going on here? I'm going to digress for just a minute and try to give you an idea of what's really going on there. It's not going to be on the exam, but I hate it when instructors say, oh, you don't need to know that. To me, it's actually kind of important to share that little bit of knowledge with you. So I'm going to digress briefly and just talk a little bit about what's happening in bonding, okay? So in the nitrogen atom, all right, when the nitrogen bonds with the oxygen in that first bond, all right, what's happening is nitrogen is sharing some electron density, right? These are covalent bonds. And you might remember covalent bonds are sharing electrons. And I prefer to use the word electron density because electrons are kind of like waves. They move around and they act out in different places. So really what's happening is that this nitrogen and this oxygen, right, are sharing some electron density. Now, how are they actually sharing it? Well, if we go back to the configuration for nitrogen, you might remember nitrogen, right? If you look at the periodic table, we have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So nitrogen is 1, 2, 3, 4, 5, 6, 7. Nitrogen is element number 7, and it has this configuration: helium, 2s, 2p, and nitrogen is 1, 2, 3 into that particular case. Oxygen looks just like nitrogen. It's a little bit further down the road. So oxygen, this is nitrogen, by the way, and oxygen is helium, 2s, this is 2p, right? So again, just to refresh, here's a gap, here's a gap, here's a gap. That's why nitrogen can form 3 bonds. Here's a gap, here's a gap. That's why oxygen can form 2 bonds, all right? Now, what's interesting is what's really happening over here, right? What's happening is kind of an overlap of orbitals, right? That's how covalent bonds form, right? And in this particular case, on the case of nitrogen, right, this overlap here is happening in a nice, even, straight way between the atoms, right? But what's happening when the oxygen atoms are bonding, right, and let me draw like a p orbital on here, right? What's happening here is that there's some p orbitals on these guys, and electron density is being shared between all 3 of those, right? So it's not just shared between the atoms centrally. This electron density is only shared between this nitrogen and this oxygen. This electron density is only shared between this nitrogen and this oxygen. However, this electron density, which is in that second bond we drew up here, it's over on this side in this picture, it's over on the left side in that picture. That electron density is really smeared out over 3 orbitals. There really isn't a way to show that in a dot structure. You just can't, right? But in real life, that electron density is smeared out over all those guys, right? That's really kind of what resonance is trying to show badly, okay? So that's kind of the concept of what's happening. Okay, now, what about this concept of formal charge? Okay, so remember I said that this is a possible picture for how you could put nitrogen and oxygen together. And this is a possible picture for how you could put nitrogen and oxygen together. And how would you think about deciding which one of those potentially is better? Well, formal charge is this thing that we use right? And there's a formula. You can look at that formula and you can ask yourself, can I figure this formula out? Go for it. I'm not really fond of that. What I prefer to do is I prefer to think about the atom as it existed as a free atom and the atom as it exists in a bond, all right? So let's consider the atoms that we're talking about in the nitrate species. Nitrogen looks like this. It has 5 electrons. Oxygen looks like this. It has 6 electrons. Oh man, that was a crappy dot. You know what? I'm gonna erase these and draw them over because I want those dots to look nicer. All right, so let me redraw those, nitrogen and oxygen, and then let me pick a bigger button. All right, come on. All right. 1, 2. All right, so those are the dots that are around nitrogen and oxygen. So just to refresh your memory, nitrogen came with 5 electrons, oxygen came with 6. Let me go back to a finer point. Okay, so let's say we drew those 2 structures as our potential resonance structures, nitrogen, oxygen, and then nitrogen, oxygen, oxygen, right? These are ions, by the way, right? The NO2 is the -1 species. And let me actually go back up here where we do our dot structures. I did put the brackets on those, okay? Got to remember when it's an ion, you have to put those dots in there. Excuse me, you have to put the brackets and show that it's an ion. Okay, so how would you know which one of these, actually, let's finish them up. So what we ended up with was we ended up with a double bond there, a lone pair there, and that. And we never finished this guy. What we should think about, okay, if I draw this dot structure, how do I make this one work? Remember, nitrogen has 5 electrons, each oxygen has 6, so that's 12 and 5 is 17. We had 18 electrons to put in this picture, right? And I get it, this puts oxygen as quote unquote the central atom, but remember we wrote NO2 minus, and so that might lead you to think that those oxygens are stuck together and you might draw this as your dot structure. So how would you know that that's not a good dot structure? Well, you draw it and then we'll try to finish up the picture, okay? So in this particular case, we would follow the same kind of rules. I've used 4 electrons. So 4, I forgot my count already. Nitrogen is 5, 17. We have 18 electrons to put in the picture, right? Is that correct? 18 electrons. Okay, so we had 18 electrons. It's the same 18 electrons if we draw this structure. For some reason, I thought I had a smaller pen, but apparently I didn't. Okay, maybe I want a bigger pen since I'm doing dots. Okay, so we've used 4. So 18 minus 4 is 14, which is 7 pairs. So I would do the same thing. 1, 2, 3, 4, 5, 6. Same deal, 7 pairs. I've used up my 7 pairs. I'm done. I got no place else to put it. Let me double check counting electrons. 2, 4. There's a dot there. You just can't see it. 2, 4, 6, 8, 10, 12, 14, 16, 18. I've used up all my 18 electrons. No problem. I'm going to have to do the same thing because the oxygen in the middle is not happy. So I'm going to have to form a multiple bond. Where you form the multiple bond is totally up to you. Let's just pick that one and draw this structure then. Well, actually, now we've got multiple structures. So or I could do this. That's different, right? Because now I'm making a double bond from a nitrogen rather than the oxygen. So that's actually a completely different structure. And 2 dots there, 2 dots there, double bond O, double bond, single bond O. By the way, these are not in resonance. Somebody know why that's not an example of resonance? Anyone want to take a stab at that? Why is that not an example of resonance, whereas this is an example of resonance?
Because nitrogen has to be the central atom.
That's one thing, but if you look at this particular picture, the double bond is between nitrogen and oxygen on one side or between nitrogen and oxygen on the other side. If we come over here, the double bond is between oxygen and oxygen on one side or nitrogen and oxygen on the other side. It's not equivalent, right? These are not equivalent structures. So here the double bond is between nitrogen and oxygen. Here oxygen. Here the double bond is between nitrogen and oxygen. So that's not an example of resonance because it's two different structures. This is an example of resonance because these are identical structures. I've just moved the double bond between one side of the molecule and another, but it's still a double bond between a nitrogen and an oxygen, right? So that's a fine line that distinguishes those. So then you got these pictures and you might ask yourself, well, how do I know which one of these is right? How do I know these pictures here? And the answer is formal charge. And the way I do formal charge is I take a pen or whatever stylus, and I circle each atom with the electrons that are associated with it, right? And what I do is I compare the free atom to the bonded atom. Now, what the heck does that mean? Well, remember a second ago, I drew the free atoms. As a free atom, nitrogen has 5 electrons around it. As a free atom, oxygen has 6 electrons around it. So in this particular circle right here, all right, in this particular circle right here, now we have to think briefly about this for a minute, okay? And here's where life gets a little complicated, and if you want to memorize the formula, you can. These electrons right here are bonded, right? So what's true about them in a covalent bond? They're shared, right? So when you're counting these electrons, right, because they're shared, you assign half to one atom and half to the other atom. That's a little thing that you have to remember, and that might make thinking about it more complicated than actually memorizing or using the formula. But keep in mind, on the quiz or the exam, you're going to have the PowerPoints, you're going to have everything in front of you. I just want to talk about it this way because I don't like just throwing out the formula because there's no basis in reality for why that formula should make sense to you, right? My method at least makes you think about what you're doing. Okay, so if I count this oxygen, it's got 2 electrons, 4 electrons, 6 electrons, and half of these bonded pairs. So this oxygen really has 7 electrons associated with it, all right? This nitrogen has 2 electrons that are a lone pair. It's getting 1 electron from this pair, 1 here and 1 here. So 1, 2, 3, 4, 5. This nitrogen has 5 electrons associated with it. This oxygen has 2, 4, 5, 6. That oxygen has 6 electrons associated with it. Okay? So now let's compare. Originally, oxygen had 6. This oxygen has 6. So what's its formal charge? Anyone want to take a stab? This is an easy one. The formal charge on that oxygen atom is, don't all jump at once.
18.
Think about this. It originally had 6 electrons as a free atom. Now as a bonded atom, it has 6. Does the number of electrons change on that guy? Yes or no? Is it the same or is it different?
Same.
The same. So if it didn't gain or lose electrons, what should its charge be?
-2.
0. You didn't change anything. You didn't add electrons. You didn't take electrons away. The charge. You know what? I saw some chatting. I'm going to see if I can't pull that chat up so I can see what people are typing, but I'm trying to find that chat box. There it is. Zero. There it is. Cedar nailed it. The charge on that guy is 0. Okay. This nitrogen has 5. It came with 5, right? So this nitrogen has 5 electrons around it now. It originally had 5. So the same thing. The formal charge is 0. All right. Now here's the fun one. this oxygen has 7, but it originally came with 6 electrons, right? If it has 7, but it originally came with 6, what does that mean it did? It gained an electron. So what should its charge be? If it gained 1 electron, what charge does that bring? A -1. So the formal charge on this guy is -1. All right. So the formal charge is -1. The overall charge on the molecule is -1. The formal charge on the oxygen is -1. So that's good. I have a negative charge on an oxygen. So now you got to ask yourself a question. Is this reasonable? Which atom would rather carry the negative charge, an oxygen or a nitrogen? And again, think about your periodic table. Here's nitrogen, here's oxygen. Which one is more likely to gain an electron, a nitrogen or an oxygen? Well, think about what they like to do. They both want to gain because they're both nonmetals, but which one's closer to fluorine, the one that really wants electrons over here?
The oxygen does.
Oxygen, right? So I put a negative charge on oxygen. Boom, that's good. I'm really happy about that. That's what I want to see. All right, let's look at these other guys. Okay, let me go back here and let me make this pen a little bit finer and let me pick a different color. Okay, so let's look at this nitrogen. 2, 4, 6, and half of the bonding pairs. That nitrogen has 7 electrons on it. How about this oxygen? 2, 3, 4, 5. That oxygen has 5. 2, 4, 6. That oxygen has 6. All right. So let's do the same math. Nitrogen came with 5 and now it has 7. So what's its charge on this? What's the formal charge on this nitrogen?
2.
Yep, the formal charge is -2. What about the formal charge on this oxygen? It came with 6 and now it's got 5. What had to happen there?
+1.
It lost 1, so this is a +1. This oxygen came with 6 and now it has 6. So what's its charge?
0.
0. All right. See a problem with this? Based on what we just said, I've got the oxygen as +1 and the nitrogen as -2. By the way, +1 and -2 adds up to -1. So the formal charges are good. But is this good to put a -2 charge on a nitrogen and a +1 charge on an oxygen? Nope. So this is actually not a very good picture. And formal charge would tell you that. If we look at the next one, all right, let's look at this one. Starting here. So this oxygen, 2, 4, 6, 7. So this oxygen has 7 electrons. 2, 3, 4, 5. This guy has 5 electrons. One, 2, 3, 4, 5, 6. This guy has 6 electrons. So if I do the same math, nitrogen has 6, it came with 5, so that means it gained an electron, so it's -1. Oxygen has 5, it came with 6, so that means that's a +1. This oxygen came with 6, and now it has 7, so that means that guy's a -1. If I add all these up, it adds up to the charge, so that's okay. But look what I've done here. I've made charges all over this molecule. I've got a plus oxygen, a minus oxygen, a minus nitrogen. That's bad, right? You really want to put the negative charge on the atom that's closest to fluorine, the one that really likes it, and you really don't want to spread charges out. So if you had looked at formal charge, this is the best structure right up here that you had drawn, and formal charge lets you figure that out, right? You could go back to the PowerPoint and you could look at this, all right? Formal charge equals valence electrons minus bonding electron pairs minus 2 times the ligand pairs. Okay, that's true. This formula here works to give you the formal charge. But when you see this, does that mean anything to you? Honestly, is there any science behind that? No, none. So if you're a tell me the formula, I'm just going to plug the formula in kind of person, go ahead and use this, right? If you are a person who kind of wants to understand a little bit, do it this way. It's more complicated, right? I get that. But next semester or in the fall, when you take Chem 111A, or excuse me, Chem 120A or 120, you'll probably do this in 120A, and it'll probably come back to haunt you in 120B. They'll just assume you know how to do it. Understanding the concept of sharing electrons evenly, right? Because these are all covalent bonds. That's why I split these bonding pairs and said, okay, this guy gets half the electrons, this guy gets half the electrons. In reality, that's not entirely true. Some atoms get more than half the electrons, but this is a model, right? So it helps you kind of look at particular pictures and say, all right, I think I can do that. Right? So that's the concept of formal charge. And you really want to use formal charge when you're deciding between, what's the possible, what's the best possible Lewis structure I can come up with. And here's a classic example of where that might come in, right? This molecule, the SCN minus molecule. I'm not going to go through this. Maybe you can work on this as a practice when you want. This is the thiocyanate ion. Thiocyanate ion, right? And if you were to start to draw we can just start briefly, right? Sulfur's in the same group as oxygen, so it has 6. Carbon's got 4. Nitrogen's got 5. This -1 means you got to add an electron, so 6 and 4 is 10. Plus 6 is 16 electrons, right? So when you draw this with 16 electrons, you're not going to be able to make everybody happy. So you're going to have to make some multiple bonds, right? And the question is, where do I put the multiple bond? Do I put the multiple bond between the sulfur and the carbon? Do I put the multiple bond between the carbon and the nitrogen? You can end up drawing a whole bunch of resonance structures for that particular picture, right? And not resonance structure. You can draw a whole bunch of equivalent kind of structures, and formal charge would let you determine which of those would be the best. All right. If we have time today, remind me and we can come back to this. But I want to make sure I get through all the stuff that we're supposed to cover. So this is an example of where formal charge can help select best Lewis structure. All right. And what do we mean by best? It minimizes separation of charge. So if you look at this picture, that maximizes separation of charge. I've got a minus over here, and a plus over here. That really spreads charge out. And when you spread charge out onto the atom, that costs you a lot of energy, and they hate it, right? If you look at this guy, I've got a -1 over on one end, and it's on an atom that really likes electron density. It's on an oxygen, so that's good. He's happy, right? And so when you're using formal charge, you want to minimize separation of charge, and you want to put negative charge on atoms that, quote unquote, like negative charge. We haven't talked about this yet. It's called electronegativity, but basically the way you figure it out is closer to fluorine. Fluorine loves electrons. The closer you can get to fluorine on the periodic table, those are the ones that really like electron density, and they're going to want to have a negative charge if they possibly can, right? So let's spend a little more time talking about that concept of resonance and how you would deal with a particular example. Another classic example of resonance is this guy, CO3 - 2. All right, so if I asked you to do the dot structure for the carbonate ion, right, what would be the first thing you would do? You would count electrons, right? So carbon's in group 4, it's got 4 electrons. Oxygen's in group 6, so 6 times 3. And then it's a -2, so I have to add 2 electrons to get my total count. So 6 times 3 is 24. 24 plus 2 is 26. 26 plus 4 is 30 electrons, right? So let's just double check. Carbon's got 4. Oxygen's got 6. You know what? I made a mistake. Good thing I double checked. 6 times 3 is not 24. 6 times 3 is 18, right? So 4 plus 18 plus 2. So I have 24 electrons to put in the picture. Always useful to double check. And let me fix that. That does not look like a 4. Okay. So again, if you're going to do this structure, which one goes in the middle? Think about the periodic table. CNOF. Carbon is way to the left of oxygen, which means carbon is more metallic, which means carbon should be the central atom. All right. And this is what I would automatically come to mind, but you might inadvertently think this, right? Formal charge will help you understand why that's not going to be the right picture, even though you could draw that, or you could do this, right? I mean, you guys could come up with all sorts of interesting things, but I want to encourage you that normally that does not mean that they're stuck together. It just means you have 3 of them on one atom. And in fact, it almost never means that those guys are stuck together. So typically pictures like this don't happen, okay? So we've got our basic structure, CO3 minus, and we've used 2, 4, 6 electrons. 2, 4, 6 electrons. So let me write that. We've used 2, 4, 6 electrons. So 24 minus 6 is 18. 18 divided by 2 is 9 pairs. Okay. So I'm just going to start here. 1, 2, 3, 4, excuse me, 1 pair, 2 pair, 3, 4, 5, 6, 7, 8, 9. I've used up all my electrons. And I got no more. Does anyone see a problem with this picture right there, right now?
Carbon isn't happy.
Absolutely. Carbon is not happy. And again, the temptation might be to say, well, carbon's not happy. Now carbon's happy. Can you do that?
No, we just added another line, right?
Yeah, you can't do that. You cannot just throw electrons in there. Even though you want to, you can't just throw electrons in there because you just pulled those electrons from somewhere. They weren't part of this original count, so you cannot do that, all right? That's unacceptable, all right? When you don't have enough electrons to make everybody happy, what do?
Just borrow.
Borrow to make what?
Make it happy with 8.
Okay, you're gonna make it happy, but in the process of borrowing another pair from somewhere, you're gonna make a multiple bond, right? So
Yes.
in order to make them happy, you're going to make a multiple bond. Now you got to ask yourself, where do I want to pull from? Do I want to pull from this oxygen to do that, which is scenario 1? Do I want to pull from that and do that, which we'd call scenario 2? Or do I want to do that, which we'll call scenario 3? Which of those do you want to do?
3.
Did you mean all 3
you have
or
to do
numbers?
all of them?
You got to do all of them. Yay. I don't know who just answered that, but somebody just answered it correctly, right? These are all equivalent. So once again, we got an example of resonance. You got to do all 3. Oh, I hate that. But you do. All right. So what does that mean? It means that in order for the correct structure for that compound, that ion, by the way, CO3, this is still a -2. In order for me to draw the dot structures, the correct dot structures for the carbonate ion, one of them is going to have a double bond here. And I'm going to spread them out evenly just because I like spreading them out evenly. And in the end, it turns out that that's really how things look. This is -1. Oops. -1. All right. Let me just check real quick on my count. Pick a color that might be seen. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And we were supposed to have 24 electrons. Okay, so we're good. So I've got 24 electrons in my picture. I'm happy. So now the next one is going to have the double bond somewhere else, where, I don't know, one of these other spots. So then the next one's going to look like this.
Good question.
Yep.
So you're just saying that if you're asked for the resonance, then you draw all three. That's it.
Well, yes, but do you think I'm going to say draw the resonance structures, or do you think I'm going to say give the Lewis dot structure and assume you will know that you have to draw all the resonance structures?
How are you going to say the second one? So give the Lewis.
Yeah, I'm going to say give the dot structure for the following compounds, and built into that is an understanding that you have that if resonance is possible, you will show me all the resonance structures.
Got it. Thank you.
Okay, so then the third possible.
Professor?
Yep.
I have a question.
All
So
right.
when it's like -2, so that means gain 2 electrons. So do you have to add 2 electrons to each atom in the compound?
Well, you did in order to make that work, and I'm glad you brought that up because I had it as -1. I don't know what I was thinking. Let me answer your question in 1 second in a little more detail. So there, that is not a dot. My pen is being poopy. Okay. To answer, that was Sammy, right?
Yes.
So Sammy, we took care of that up here. When I counted electrons, the fact that the carbonate had a -2 charge, here's where I took care of that when I got this total electron count of 24. So that means any picture I draw resonance-wise has to have 24 electrons. And so that's why I was counting. I only counted this first one, but I could count all the other ones, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I just want to make sure every one of them has 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So because I counted the first time I did it, I know every one of them has to have 24 electrons. And because I know that it's an ion, I have to show the charge on every one of those. So I hope that answers your question. In order to make those pictures work, I did have to add 2 electrons, yes. So that's basically resonance, and you're going to run into resonance in a variety of places, but almost exclusively, you're going to run into resonance when you have more than one place to make the same double bond, okay? So remember, when we did this is not resonance because this is an oxygen-oxygen double bond, and this is a nitrogen-oxygen double bond. So that's not an example of resonance. In this case, this is resonance because it's always a carbon-oxygen double bond, and they're all equivalent. And again, what this is saying is that in real life, none of these is right. The real picture has carbon surrounded by 3 oxygens, and then there's a p orbital on these guys, and it's sharing electron density above it and below it, right? That's really what's happening. That resonance is a smeared out electron density picture. It's really hard to draw in 2 dimensions. And so what this is trying to indicate to you is that the electron density is really here, here, and here all at the same time. That's what resonance is trying to indicate. All right. It's not indicating that sometimes it's here, sometimes it's here, sometimes it's here, or it's moving around like the spokes on a wheel. None of that's true. It's really smeared out over this whole picture all the time at the same time, right? And that really explains how they behave chemically too, in terms of bonding and other things, which you're probably not going to have much time to get into in this class. Okay, so let's go back to the PowerPoint. Okay, so if you're comfortable with this formal charge definition, more power to you. I hate it, but I'll put it there, and I'm not going to go even through the practice just because I don't like it at all, but it's there. All right. And there's some other ones you can practice, like the PO4 - 3. If you drew this structure, right? If you drew the structure of PO4 minus 3, it looks good, right? But the formal charges will be off, and that helps you understand why you have to put a multiple bond in there. And then, of course, if multiple bond is there, then that means you have to draw resonance structures for it. Okay. I don't want to get to this next topic yet, VSEPR geometry. We don't want to talk about geometry of molecules yet. I want to talk about periodic trends. So let me stop this share and let me go back to the other PowerPoint that deals with, let me go back to the structure that talks about, trying to find the one that deals with, whoa, I'm not sure what just happened there. I'm not sharing my screen just yet, so I will momentarily. All right. So let me share this one with you. Share. Send a copy. Accept mobility. Oh no. Heck. No. Okay, so now I'm going to share my screen again. Minimize this. Back to Zoom. All right. Okay, I'm going to share my screen here. All right, can you guys see my screen now?
Yes.
Awesome. Okay, let me put the chat back up so in case you guys have something to say to me. All right, so periodic trends. Periodic trends are something that we kind of need to talk about. But again, before I go through the slides, let me just go back to my previous notes and create a new slide just because I want to refresh your memory about where we're headed. So periodic table. All right. Periodic trends are just that. They're things that are observable on a general scale as you move through the periodic table, okay? So like, let me give you some examples of things that you may already know about the periodic table. They wouldn't necessarily be called trends, right? But you probably already know them. So as you go from left to right in the periodic table, what's happening to the mass of an atom? As you go from left to right in the periodic table, what's happening to the mass of an atom?
Does it get bigger?
Yeah, they're getting bigger, right? So that's something that you could consider a trend, but it's not really a trend because it's happening exactly, right? Every time you go one atom over, you're adding protons and electrons and neutrons, so the atoms are getting heavier, right? But there are things in terms of properties of atoms that change repeatedly as you go through the periodic table, right? And they're really useful for predicting and understanding other things about the periodic table. So that's what I mean by periodic trends. So let's go back to this and let's talk about some of those periodic trends, right? So this is the modern periodic table of the elements. And again, on the exam, or yep, it's still January 9th. I'm living in the past, Kay. I just can't. It's Groundhog Day for me. Every day is January 9th. So modern periodic table. Again, the things that are useful and the things that I consistently refer to, I want to point out group 1, group 2, group 3, 4, 5, 6, 7, 8. The A is not super important to me. So I'm often going to refer to this as group 1. I'm going to refer to this as group 2. I'm going to refer to this as group 3, group 4, group 5, group 6, group 7, group 8. I'm going to refer to these as the noble gases. I'll refer to these as the alkali metals, the alkaline earths. These are the transition elements, right? These are the halogens, group 7. So they all have kinds of names. These guys down here are the rare earth elements. Transition elements, you'll recall, are kind of hard to predict because, well, they have d orbitals and their electrons can be a little bit soft and mushy. So sometimes they can lose 2 electrons, sometimes they can lose 3. But there are general things about the periodic table that we've talked about and used on a number of instances, all right? So you remember all that stuff. That apparently didn't come over very well, but we just mentioned that already, chemical families, right? So this is a family, right? The alkaline earth metals. And you may remember that we talked about the fact that they behave similarly chemically, right? Well, why is that? Well, they're all in the S block. They all have one S1 as their configuration, right? They all form similar compounds, right? So if I was going to combine hydrogen with oxygen, I would get H2O. If I was going to combine lithium with oxygen, I would get Li2O. If I was going to combine sodium with oxygen, I get Na2O, right? They're a family. They all behave the same way. They have similar properties, okay? They're not the same. They're similar, right? And the properties change predictably as you move through the periodic table, right? So other families we talked about, again, I mentioned those. These are the alkaline earths. These are the transition elements. You might also run into something called the representative elements. The representative elements are all of the elements in the S and the P block. So if you hear that term representative, it means any of those elements in the 2 circles, S and P filling elements. Okay. So some characteristics that are definitive about metals, right? These are not periodic trends. They're just general characteristics. And we've not really taken a lot of time to talk about these. I suspect you know most of these. You know that metals tend to be shiny. You probably know that they conduct heat and electricity very well. You may not remember this one very much. Metals tend to be malleable, which means we can pound them into sheets. Right? Now you might say, well, aren't metals hard? Actually, the real definition of metals is that they're actually kind of soft. Sodium metal can be cut with a butter knife. It's actually very, very soft. Once you get into the transition metals, they tend to get hard. So lithium is a pretty soft metal. Sodium is a very soft metal. Potassium, very soft. They're also ductile, which means you can draw them into wires, right? Which is something you really can't do with nonmetals. So nonmetals, these guys, if you try to hammer them, they break. They're very brittle. They don't like to be hammered into sheets. They don't like to be drawn into wires, right? Typically, that's the characteristic of metals, right? It doesn't mean you can't do that with these elements on the right-hand side. It just, you can't do it very easily. It's not a typical characteristic of nonmetals, okay? And they're typically solids at room temperature. But again, I think you probably knew that they were solids at room temperature. Nonmetals are on the right side of the periodic table, and they're not, I don't want to say opposite or contrary to metals, but they appear that way, right? So nonmetals do not have a metallic luster. What does that mean? That means they're dull, okay? So again, these are generalities. If you've ever seen a chunk of silicon, of pure silicon actually looks like a metal. It's kind of shiny and has a luster like a metal, but it's also very brittle. If you hit silicon with a hammer, it shatters into a bunch of little pieces. So these are generalities, but for the most part, nonmetals tend to be dull, right? They also tend to be very bad conductors of heat and electricity. And there's another word for this. If something is a bad conductor of heat and electricity, what one word do we use to describe those? Anybody know that?
Insulators?
Yep, these are also called insulators. So they're good insulators, right? They don't conduct heat, electricity. They're also brittle, and they can be a solid or a liquid, a gas at room temperature, okay? Once again, these are generalities. Mercury is a metal, but it's a liquid at room temperature. Okay. Gallium is a metal. It'll melt at body temperature. If you have gallium in your hand, it will melt at 37 degrees Celsius, right? So generalities, I want you to be clear on when we talk about properties, we aren't saying they're absolute. We're saying they're kind of generalities. But most of them fit that property, right? And that's useful for us if we're going to say things about them. Semi-metals or metalloids. So if you remember the stair-step line, these guys right here, they kind of have properties of both. And that, remember I mentioned silicon. Silicon has a luster. Silicon is a semiconductor. It conducts electricity kind of okay. Carbon's kind of touching that line. Carbon, if you know anything about carbon, it has multiple forms. Carbon can exist as diamond. It can also exist as graphite. Diamond's a really good insulator. It's really hard and really brittle. Graphite, can use as a lubricant. And graphite, based on its crystal structure, can conduct electricity in one direction, and it's an insulator in another direction. So it's got some really cool properties. And a number of these guys are used in semiconducting devices: silicon, phosphorus, arsenic, right? Lots of properties, antimony, tellurium, lots of properties that allow them to kind of go both ways. And we make use of that in quite a bit of the chemistry that's going on in your everyday life. Okay. Okay. So here's some trends about metals. These are periodic trends, right? So again, across a period from left to right, what do we mean by a period? A period is a row. A period is another name for a row. So this is the first period, this is the second period, this is the third period, this is the fourth period. So period goes to the right on the periodic table. That's actually why the table is called the periodic table, because what happens is chemical properties repeat in a periodic fashion, right? It actually is named that for a particular reason. So across the periodic table, metals become less reactive. So as you go from left to right, metals are less reactive. Okay, so that's something that should be interesting to you. Why do you think metals become less reactive as you go from left to right? Well, let's just pick these two guys, sodium and magnesium. Why would sodium be more reactive than magnesium? Well, in order for sodium to react, right, it's got to get rid of that one electron. In order for magnesium to react, it's got to get rid of 2 electrons, right? Sodium forms a +1 ion, magnesium forms a +2 ion. It's got to get rid of more electrons as it reacts, and so it's a little bit more difficult for it to form an ion. So metals tend to become less reactive as you move to the right because it's harder to pull electrons out.
A quick question.
Yep.
Does that have to do with ionization energy too?
We're going to talk about ionization energy, but ionization energy is related to that. Absolutely. When we're talking about ionization energy, we're talking about pulling electrons out, and the more electrons you have to pull out, the harder it is. And so, yes, the ionization energy increases.
So sodium will be less compared to magnesium.
Yes, sodium has a lower ionization energy than magnesium. And actually, we have to be careful because sodium has 1 ionization energy. Magnesium has 2 because it gets rid of 2 electrons. So you pull 1 electron out, it's kind of easy. To pull the second electron out, it gets progressively harder. So we'll talk about that trend in a minute. Okay. This is actually maybe contrary to something you would think. As you continue to go across the periodic table and you enter nonmetals, they become more reactive as you go to the right. So if we go back to our periodic table, as you're going across, the metals become less reactive. But once you get into this part of the periodic table, the nonmetals, as you go to the right, they become more reactive. And it's a similar thing, right? Because if you think about nonmetals, they want to gain electrons to fill the p orbitals. And, oops, I shouldn't do it that way. Right? And as you recall, as you go to the right in the periodic table, you're successively adding electrons. So we'd have 1 electron in boron, 2 electrons in carbon, 3 electrons in nitrogen. Again, remember, in order for them to react, they want to fill up these empty places. So boron would have to fill up a whole bunch of empty places. As you go to the right, there's fewer and fewer empty places to fill, right? So oxygen only has to fill 2 places, so he's more reactive. Fluorine only has to fill 1 place, so he's even more reactive. In fact, fluorine is the most reactive because it only needs 1 electron to become like a noble gas. And so it's the most reactive element in terms of nonmetals. All right. Noble gases don't react, so we don't worry about them. Noble gases are unreactive. We just said that. Metals lose electrons. We said that. We showed that. And we saw that in terms of an orbital notation. And when they lose electrons, they form cations, a positive ion. And when they react, so M plus X, it forms a positive ion. That's what that means. So it forms an M plus, that was supposed to be a superscript, but when I imported it, it lost that superscript. Trying to see, okay, we can't see, yes, okay. Nonmetals conversely gain electrons and they form a minus ion, okay? And we've seen that already, right? It just kind of makes sense from where you are in the periodic table. A metal will lose electrons and go backwards to the closest noble gas. Nonmetals gain electrons and go forward to the next noble gas. These become cations by losing electrons. These become anions by gaining electrons. And the clue to figure out how many they gain or lose is to find their position in the periodic table or draw the dot structure or look at the orbital notation. Right? They're all interrelated and they all kind of share the same information. Okay. Same thing is true about compounds of similar elements in the periodic table, right? So we mentioned this earlier. Lithium, sodium, and potassium are all group 1 metals. And so when they combine with chlorine, the formulas are identical. It's not a coincidence that lithium chloride, sodium chloride, and potassium chloride are all the same kind of formula. They also have similar properties, not the same, but they have similar properties, right? If we go to the next family, beryllium's +2, magnesium's +2, calcium's +2. So when you combine them with some other ion, like hydroxide, the formula is the same, OH2. And again, I apologize for the fact that that's not a subscript, but when I imported it into notability, I somehow have lost that subscript view, all right? And again, you can probably see this. Formulas of compounds vary systematically across a period. So lithium chloride is LiCl, BlCl2, BCl3, CCl4, right? So we're seeing a periodicity in terms of the compounds that they form with that particular formula. These guys, these are a little more complicated and it's maybe not as obvious to see, right? But when nitrogen combines with chlorine, right, it only needs 3. Oxygen only needs 2. Chlorine combining with fluorine only needs 1. These are ionic compounds, and these are covalent compounds. So these are not necessarily easy to predict, and we talked about that earlier. So I wouldn't ask you to predict something like that. Okay. So there's some things that you might be asked to do. Identify elements using their location on the periodic table, right? So a question might be, an exam question might be, what's an alkaline earth metal in the 5th period? So alkaline earth means you're in the second column, and the 5th period means you're 5 down. So if we go back to our periodic table, I might say, okay, identify an alkaline earth metal. So that's these guys. And in the 5th period, so 1, 2, 3, 4, 5, that puts us there. So it's kind of like doing a puzzle. These are the 2 intersecting points of that particular statement. So it might also say, okay, pick a pick a halogen in the second period, right? So halogens are over here. This is the first period. This is the second period. A halogen in the second period would be fluorine. Halogen in the third period would be chlorine, right? So something like that would test your ability to understand the periodic table. And I suspect you'll have practice questions on the periodic table. Okay, so special element groups, we mentioned this. The main element groups are what we talked about. Transition metals, rare earths are down at the bottom. We mentioned this a bunch of times. The electron configurations are related to their position and their reactivity. We did not do anything with quantum numbers, so don't worry about quantum numbers. If you encounter homework questions about quantum numbers, let me know and I will get rid of those questions because they're not going to be on the exam. Okay. I think valence is pretty easy to understand. The valence trends across the periodic table. It's really about getting a noble gas configuration. You always want to get 8, whether you're losing electrons to get an inner shell of 8 or gaining electrons to get an outer shell of 8. Okay, so here's some actual trends that probably are going to be completely new to you. And they're actually really useful in helping us understand some of the other things that are going on in the atoms, all right? So I'm going to expand this a little bit. Hopefully you can see this. This is a chart of atomic radii, okay? I know they've drawn the full sphere of the atom, but it's really just the radii. And take a minute and look at this picture, all right? The colors don't really mean anything, right? But let's look at a family, okay? Let's look at group 1, which is the family right here. What do you notice about the size of the atom as you go from top to bottom? This is an easy question.
Gets bigger.
Gets bigger, okay? I agree with you totally. Do you see anywhere in the periodic table where that trend is violated?
Noble gas.
Yeah, there's a little bit of the noble gas issue right down here, right? But for the most part, that trend is there. It's not perfect, and I agree with you, Min Sung. It looks like it's violated, but in general, right, periodic trends are generalities. In general, do atoms seem to increase as you go from top to bottom? Yes or no?
Oh.
Yes.
Yes. Okay. So that's a periodic trend. As you go from top to bottom, atoms tend to get bigger in size. Now, the real question is, why are they getting bigger? Well, the answer
They have more shells.
Absolutely, that is the correct answer. Every time you take a step down in the periodic table, every time you go one step down, so this is n equals 1, this is n equals 2, this is n equals 3, right? Every time you go down one step in the periodic table, you've added an energy level to the atom, which by default makes the atom get bigger, all right? So that should make sense to you. So that's a good periodic trend. As you go from top to bottom, the atoms get bigger. All right, I'm just going to get rid of this stuff because I don't need that written all over. All right, what do you notice as you go from left to right? This one's a little bit more complicated. Overall, what's happening in general?
Getting bigger.
Pardon?
Bigger?
Well, look at the pictures.
Smaller.
Yeah, they're getting smaller. As you go from left to right, the atoms are getting smaller. Now, I want to ask you guys a question. Does that make sense?
Isn't it because like...
No, I know why it is, but let's just answer my question. I don't want you to explain what's happening. Does it make sense? What are you doing every time you go from the left to the right?
Adding electrons.
Electrons? What else are you adding?
Protons.
What else are you adding?
Neutrons.
Okay, does it make sense if you're adding all that stuff? Does it make sense that the atom should be getting smaller?
No.
No, what happens to you if you keep eating? Do you get smaller?
Bigger.
Yes. No.
All right. So something weird must be going on here, right? The trend is clearly seen. As you go from lithium, lithium's got a radius of 3. We won't worry about the units in this particular case. Beryllium's got a radius of 4. So even there, in going from lithium to beryllium, they get smaller. Then notice there's actually boron is 5. Oh, sorry, that's the atomic number. The number of the sizes below it. So lithium's 11. I think they're picometers. Beryllium is 12 picometers. Oh, wait a minute. No, those are the numbers of the one above it. They're not showing actually, so we just have to guess about the sizes. So I apologize. Those are not the numbers of the sizes. Those are just the atomic numbers. So if you look at lithium to beryllium, the picture looks smaller. And as you go here, it looks smaller. But let's look at the next row. Sodium, magnesium. Magnesium looks smaller. And then aluminum looks smaller, right? No problem. Smaller, 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 bigger, right? We'll talk about why those guys are bigger in a minute, but maybe I think you can already figure it out, all right? Again, what's happening as we go from left to right? We're adding electrons and protons. That makes sense. Does somebody know why? Minsung, I think you were going to try and tell us. Why do they get smaller as you go from left to right?
No, actually, I don't know, but I'm guessing that is it because it's turning to S block to P block.
Say that again.
I'm not sure about like because I don't know the correct answer, but I'm guessing because like at the left it's like S block, but at the right it's gonna convert to P block.
Well, actually, the P block is bigger than the S block, so that's a good guess, but it's kind of counterintuitive. Let me draw a picture for you guys and see if this makes sense.
Does it have to do with charges?
It does have to do with charges.
So the more electrons, protons, the more they attract, so the smaller the radius.
So let's say we got lithium, and actually let's not do lithium. Let's go sodium and magnesium.
That would be Coulomb's law.
So sodium is 11. Yep, physics guy, he gets it. Sodium is 11, magnesium is 12. Okay, so this has 11 pluses. 11 protons. This has 12 protons. It's got some neutrons, which I really don't care about. Why don't I care about the neutrons? Because they're crammed into the nucleus, and the nucleus really doesn't make up much of the atom. So it's got some neutrons. This one has 11 electrons. This one has 12 electrons, okay? So now if you think about attraction, right? Where is the attraction greater? Is there a greater attraction between 11 plus and 11 minus, or a greater attraction between 12 plus and 12 minus? And this is where the answer comes into play. Where is this force of attraction greater?
Well,
yeah, this attraction is greater than this attraction. So if the attraction between these particles is greater, what's going to happen to the ability of the electrons to move away from the nucleus? Well, if this is my nucleus, 11 plus, and this is my nucleus, 12 plus, the nucleus is maybe slightly larger, right? My electrons are going to be out here. These electrons are going to be pulled in closer. I've exaggerated the picture, right? And I know they're in S&P, but they're going to be pulled in closer because the difference in charge here is bigger, all right? The difference in charge is bigger, so that electrons get closer. There's other rules that come into play in this as well. There's a term called shielding, right? And we're not going to spend any time talking about that. That's a quantum mechanical thing, but it basically has to do with electrons hiding each other from the nucleus. And so the trends aren't exactly what we would predict them to be, right? But if we go back to what we saw in the real trends, you can see that generally speaking, from left to right, they get smaller, right? With the exception, of course, when you get to the end here. And why are these guys getting bigger? Well, because I filled up that shell, right? I filled up the shell completely, and the atom can't hold on to it as well. So once you get all the way to the end, right, the atoms get bigger, All right, so that's the atomic radii. So the general trends in atomic radii is that as you go down, the radius increases. As you go across, the radius decreases, right? That's atomic radii. Not to be confused with ionic radii. So let's go to a new sheet. And let's use the same two things. Sodium. Sodium has 11 protons and 11 electrons. Magnesium, 12 protons and 12 electrons. And now let's talk about the ions that those guys make. Sodium plus 1 has 11 protons and how many electrons? Come on, you math geniuses. If I lose 1 electron, how many do I have left?
10.
10.
10. 10 electrons. And magnesium, what ion does magnesium commonly form?
2 plus maybe.
Yeah, plus 2,
Plus
yeah.
2, absolutely. And it has 12 protons in the nucleus. How many electrons does magnesium plus 2 have?
10.
10. 10 electrons. Interesting. Remember the word for this?
Same. Equal.
Come on. Come on. Remember the word for this.
Equivalent.
No. Keep trying.
Does it start with an R?
It starts with an I. So what?
Isotopes? No.
Nope, isotopes have the same number of neutrons.
Isometric?
Isoelectronic.
Oh, yeah.
Right? These ions are isoelectronic. They have the same number of electrons. They're going to have the same configuration, right? Sodium plus 1, magnesium plus 2, both have the same configuration, right? And what is the configuration? What atom does sodium plus 1 look like? And what atom does magnesium plus 2 look like? Think about the periodic table. Here's sodium, here's magnesium. When they lose electrons, what do they look like?
Fluorine.
Not fluorine.
Neon.
What element did I just circle?
Neon.
Neon, right? So remember, when metals lose electrons, they go backwards to the closest noble gas. So these are isoelectronic with neon, right? They have the same configuration as neon, right? And that would also be true for what other positively charged metal ion will look just like neon? Anyone? How about this guy? What atom is that?
Aluminum.
What ion does it form?
Al3 plus.
Aluminum plus 3, which means it loses 3 electrons. So it loses 1, it looks like this. It loses 2, it looks like this. It loses 3, it looks like that, right? Aluminum plus 3 looks just like neon. So it would also be isoelectronic with neon, right? Okay, so anyways, we were talking about the size of the atom, right? So as you go from aluminum or from sodium to magnesium, right? This has a greater charge, right? The plus 12 and the minus 12 are attracted more strongly than the plus 11 and the minus 11. So magnesium is smaller than sodium. So if I was going to draw an atom, here's my sodium atom. Here's my magnesium atom. It's smaller. Now we're going to talk about the ionic radii. This is the trend in the radius of the ions. So let's just for fun say this is the Na+1 ion. Before we even think about magnesium, let's think about comparing the sodium. Actually, you know what? Let me erase this. I don't want to pretend to give you some kind of. All right. So here's my picture, roughly drawn, just made it up. That's my sodium atom, right? How should the sodium ion compare in size to the sodium atom? Don't answer immediately. Think about what's going on here. Think about there's an attraction between +11 and -11 in the atom, and there's an attraction between +11 and -10 in the ion. So what should be true about the size of the ion compared to the size of the atom?
Smaller.
Yes, it should be smaller. So if this is the size of my sodium atom, my sodium ion should be smaller. So I'll make it smaller. What's the actual size? I don't know. It's probably on the slide. I'll show it to you in a minute. Okay. So magnesium +2 should be smaller than magnesium atom, right? Okay. So magnesium, well, that's going to be kind of hard. I made that pretty small. Let me make this bigger. So it's still smaller than, this is still smaller than this. All right. What should be true about the size of the magnesium atom and the magnesium ion? So Mg +2 ion, and this is your clue. So compare the magnesium ion to the magnesium atom. Here's my magnesium atom. What should I draw for my magnesium ion? Should it be bigger or smaller than the magnesium atom?
Smaller.
Smaller. Okay, now let's think about comparing to what I did with sodium. I made sodium smaller. Should I make magnesium smaller to the same ratio, or should magnesium shrink more or less than sodium shrink?
More.
Why?
That's just-
Why? You're right. It should shrink more than the sodium ion shrink. Why should it shrink more?
The difference between proton and electron.
Yep,
Sodium
absolutely.
got like one difference, but magnesium got two difference.
This is a +11 to -10. This is a +12 to -10. There's a much greater attraction between these guys. So when I draw the magnesium ion, it should be substantially smaller. So now you've automatically gotten this trend in as well, right? As you go from here to here, these guys go smaller as well. So let's go back to the periodic trends. Let me shrink this. This is all about atomic radii. Let's go to the next slide and look at ionic radiuses. Now, I didn't do the nonmetals, so you're going to get the answer right here in front of you, but look at what happens with the metals. Keep turning my pen off. Look at what's happening with the metals. As I go down, right, as I go down within a periodic, they still get bigger. Okay, no problem. But here's lithium plus. That's the size of the lithium ion. If we go back and we look at, oh, it's not listed here, so we can't actually make the comparison. That's kind of cruddy. I would have thought it would have been in there. Well, I guess you got to take my word for it. I'm going to have to find another slide because that actually doesn't help you. Really, what you'd want to be able to do is compare these to these. You'd want to see what's the size of the lithium atom compared to the lithium ion. I apologize, that's not the best comparison. What about this? What's happening over here? Look at the N-3 compared to N-3 compared to just the plain old nitrogen. Nitrogen's really small over here. The N-3 is pretty big. Why do you suppose these guys are getting bigger? Well, think about what happens when you make an ion from a nonmetal. So if I'm going to take nitrogen and make the ion of nitrogen, which is N-3, right? And again, why does nitrogen gain electrons? Let's just refresh our memory. 1s, 2s, 2p, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. There's nitrogen. That's the configuration for nitrogen. If I'm going to make the nitrogen ion, I'm going to put an electron there, an electron there, and an electron there. I'm going to add 3 more electrons. Am I doing anything to the nucleus of nitrogen when I add those 3 more electrons?
No.
Nope. So can the nucleus hold on to those new electrons as tightly as they could to the original electrons that nitrogen had?
No.
Nope. So what's going to happen when you make an anion from an atom? So if this is, yep, it's going to get bigger. So if this is the nitrogen atom, the nitrogen -3, and I've exaggerated this, is bigger, right? So now you've got some trends that you can remember. So for a metal, the ion is smaller than the atom. For a nonmetal, the ion is bigger than the atom. And within the metals, as you go across, the atoms get smaller and the ions get smaller. For the nonmetals, as you go across, generally speaking, the atoms get smaller. But what about the ions? As you go across, what happens to the ions when you're talking about nonmetals? They get bigger. All right, so that's a periodic trend. Now, one of you, I don't remember who it was, talked about this thing called ionization energy, right? What is ionization energy? By definition, it's the energy required to remove an electron, right? And I'm not going to say any more than that. It's just the energy required to move an electron. Okay? Ionization energy is the energy required to move an electron. We would draw that as a chemical equation, something like this. Atom, and then on over the line, we'd put energy goes to ion plus an electron. And it goes to a positive ion, right? Because we're removing electrons. So ionization energy does not refer to gaining electrons. It only refers to losing electrons. Right? What if you're going to form a negative ion? What do we talk about then? Gaining electrons is called electron affinity. Right? That's written like this. Atom plus an electron goes to an ion, in this case negative, plus energy.
Question.
Yep.
So Inhibiting and absorbing only has to do with photons and not with electrons, right?
Say that again?
Because from the homework, I remember running across inhibiting and absorption of either electrons or photons.
Yeah.
For energy levels.
Yeah, if you absorb an electron, yeah, if you absorb energy, you would move electrons to higher energy levels, and if you absorb a photon of a high enough energy, it will completely ionize that electron. It will remove it completely. So removing electrons deals with absorbing energy. Adding electrons typically always is favorable, and it releases energy.
Okay, so it's related?
Yep.
Okay.
Okay, so just to remind you, ionization energy is the energy you have to put in. Electron affinity is the energy you get out. All right, so this is energy in, this is energy out. Right, that means this is not spontaneous. Electrons do not just fall out of atoms. But if you had an electron and you put it near an atom, that atom will grab onto that electron happily and liberate some energy, right? So atoms like to gain electrons. Even metals, they don't mind gaining electrons, right? They just give up electrons more readily, okay? And those terms are electron affinity and ionization energy. And this is the generic representation of the equations for those guys. And just as you would imagine, there are trends for those in the periodic table, and they're really related to things we've talked about already. All right, so let's talk about ionization energy and how you might think it would vary in the periodic table. So let me just, once again, draw our periodic table. And these are trends, so I'm just going to kind of generalize, okay? So as you go this way, and as you go this way, let's talk about ionization energy. And keep in mind, ionization energy is energy to remove an electron, okay? Let's start with this one. What do you know about atoms as you go down in the periodic table? Tell me some things that happen to atoms as you go down in the periodic table.
Get bigger.
They get bigger. Okay, let's focus on that. So here's, I'm going to exaggerate. Here's what happens as you go down in the periodic table. The atoms get bigger. All right, let me draw an electron in each one of these, because these are all in group 1s. These are all in the group 1, so they all have one electron. So here's an electron, here's an electron, here's an electron, here's an electron. By the way, they don't have one electron, they have one valence electron, okay? And let me put in the nucleus. Let me put the nucleus in black. There's the nucleus on that guy. Oh, that didn't work. Let me put the nucleus in black. There's the nucleus, there's the nucleus, there's the nucleus. The nuclei are getting slightly bigger as I go, but not substantially bigger, okay? So here's an easy question. We'll call this 1, 2, 3, 4, 5. In which of those is it going to be easiest to pull out that purple dot representing the electron? 1, 2, 3, 4, or 5?
5.
Why?
It's further away.
Yeah, it's farthest away from the nucleus. It's not held very tightly, okay? So this is the easiest electron to pull out. So what's the trend in ionization energies as you go from top to bottom in the periodic table? The ionization energies, okay, remember the ionization energy is the energy required to remove an electron. You said this was the easiest one to pull out, so what's true about the energy?
Decreases.
It decreases. This is the smallest, right? So as you go down in the periodic table, the ionization potential decreases, which means it's easier to pull an electron out, okay? That parallels what we know about reactivity. As you go down in the periodic table, metals become more reactive. Why? Because they like to get rid of these electrons so they can look like a noble gas. So lithium, sodium, potassium, rubidium, cesium, francium. I don't know if you've ever seen the video, but you can go online and look at it. You can see a video of them taking lithium and putting it in water, sodium and putting it in water, potassium, rubidium, cesium. You're not going to see francium because it's radioactive and there's not a whole lot of it around. But if you see lithium thrown in water, it doesn't do much. If you ever seen sodium in water, it kind of skitters around on the surface. If you've seen potassium thrown in water, it skitters around on the surface and then it bursts into flame. If you've seen rubidium or cesium thrown into water, right, these guys basically explode the second they hit water, right? So they get more reactive. And the reason they get more reactive is because it's easier to remove the electrons, right? Which means the ionization potential is smaller, right? So that's the first trend. As you go from top to bottom, ionization potentials decrease. Why? Because the atoms are bigger. It's just easier to pull electrons out, okay? Without me drawing anything or saying anything, what do you think is true about the ionization energy as you go from left to right? Well, think about what happened here. What happened to the size of the atoms as you go down? The atoms get bigger. What happens to the size of the atoms as you go this way?
So it gets smaller, so it goes from small to big.
Yep, the ionization, or as you go from left to right. Yep, as you go from left to right, the ionization energy increases, right? Because the atoms are getting smaller. The smaller the atom, the harder it is to pull an electron out of it. So as you go from left to right, the ionization potential increases. Okay, it gets harder and harder to pull electrons out. Okay, let's talk about electron affinity. So electron affinity is the energy released when you put an electron into an atom. Now, before we draw anything, remember, electrons are negatively charged and the nucleus, and oh my gosh, and the nucleus is positively charged. Where do these guys want to be in relation to one another in real life? If I took a plus charge and a minus charge and let them go, what are they going to do?
Attract it.
Yep, they're going to attract each other, right? They're just going to fly together until they're touching, until they're happy, okay? Right? That's what electron affinity is about. When I take an electron and I let it come close to a nucleus, it's going to liberate some energy. The closer the electron can get to the nucleus, the more energy it's going to release, okay? So as I go down the periodic table, right? As I go down the periodic table, will electrons be able to get closer to the nucleus or not as close to the nucleus if I add an electron to an atom?
Not as close.
Not as close, okay? So they won't release as much energy, right? So what's true about electron affinity as you go down the periodic table?
Decreases?
Yep, it decreases.
Yeah.
And again, the reason is because these atoms are getting bigger as you go down. And if I add an electron to that picture, right? In the case of all these, I add an electron. And if here's my nucleus, here's my nucleus, here's my nucleus, here's my nucleus. In the first case, in the case of a small atom, that electron I added can get close to the nucleus. That releases more energy, so it's more stable, so the electron affinity is larger. As you go down the periodic table, they can't, right? What about, again, make a prediction, going left to right? Think about the size of the atom. What happens to the size of the atoms as you go from left to right?
Smaller.
The atoms get smaller. So what's going to be true about an electron that I would add to this atom? As I go from left to right, will the electrons be able to get closer to the nucleus or not as close to the nucleus?
Close.
Closer. So what's true about the electron affinity, the energy that's released as I go from left to right?
Bigger.
Absolutely. Right? So the reason I do it this way, guys, instead of just presenting it to you, is I propose that these concepts that are related to periodic trends are really easy to understand if you remember this. If you remember the general trend in size of the atoms, you can almost, without exception, tie that to any of the periodic trends. And once you think about that, then you can make those connections without having to memorize things. And again, I get it. You can look things up when you're doing the exam. Fine, whatever. Look it up. But if you look it up, you haven't learned it, right? So I'm trying to help you get ready for next semester, and understanding how periodic trends are related to the size of the atom is crucial for you because that'll stick with you. It's much easier to remember this and this. Atoms get smaller from left to right. Atoms get bigger from top to bottom, right? How does that impact all of the other periodic trends? Well, all right, they're pretty much straightforward. So if we look at ionization energy, right? Oh, by the way, IE is the same thing as IP. I called it ionization potential, ionization energy. They're the same thing, all right? So it gives you the definition there. They increase going across, they decrease going down, but now you know why that is, right? Electron affinity, same story. It increases going up and it increases going to the right. We're trying to put electrons into an atom. What atoms like to gain electrons? Small atoms like to gain electrons. What atoms like to lose electrons? Big atoms like to lose electrons. So if you remember where the big atoms are, you know they're going to really lose electrons. If you remember where the small atoms are, they don't want to lose electrons. Right? You remember the trends in size, you can pretty much remember these trends. I won't say without exception, but I will say that they're pretty much there. There's a few exceptions, but they're not a whole lot. And again, if you look at this, right, if you think about electron affinity, here's something that you can, I suppose, think about. So remember, electron affinity is the energy released when you add an electron to the atom. Boron is 27, carbon is 123, nitrogen's not, nitrogen's 7. So it's getting bigger, and all of a sudden it goes down. Why does it go down? Well, think about what's happening with nitrogen. Nitrogen's a half full configuration. This is the 2p. So nitrogen has this configuration. If I want to put another electron into nitrogen, it has to pair up and go here, right? Whereas if I'm putting another electron into boron, it would go here. If I'm putting another electron into carbon, it would go here. So there's open spaces for those electrons to go, right? So generally speaking, it's going down. Then it goes up, and you can see the trend continues. So there's little bumps in the trends, but generally speaking, right? See this trend? Electron affinity increases. Electron affinity increases. These are generalities. You can always find exceptions, right? And you can read about those exceptions, but the generality is what's important, right? Here's this last thing, electronegativity. This looks a lot like electron affinity, but it's not, and this is a really important term. So let me go back to my notes, and I want to talk briefly about electronegativity. What the heck is electronegativity? Looks a lot like electron affinity, but it's not the same, all right? So that's the first thing you got to get in your head. They look the same, but they're not the same. To refresh your memory, here's an atom with some electrons. If I take an electron from out here and I put it into that atom, that's electron affinity. Electron affinity is adding an electron to an atom. Electronegativity refers to shared electrons in a bond. So you should never talk about electronegativity unless you're talking about electrons in a bond. So here's an example of a bond, right? These electrons are shared between hydrogen and oxygen. Do you imagine that they're shared evenly? What do you think? Yes or no?
Yes.
Yes.
Okay, that's a good guess. You would say yes, they're shared evenly. But now let me throw in some of the other things we know about this. Hydrogen's a little teeny guy with one proton in the nucleus. Oxygen, if we go back to our periodic table, oops, let's go back to the periodic table up here, and let's look at the atomic radii. All right. So hydrogen's really small. Oxygen's pretty small as well, right? Oxygen. But if you're going to compare these guys, is there a big difference in the size between an oxygen atom and a hydrogen atom? Yes, no, big size difference?
No.
No, there's not much of a size difference, okay? But hydrogen's nucleus is +1. What's true about the oxygen nucleus? How many protons are in the oxygen nucleus?
6.
6. Okay? Do you really think that this +6 is pulling on these electrons the same as this +1 is pulling on those electrons? Yes, no?
No.
No. Absolutely not. Which one is pulling on the electrons more?
Oxygen.
Oxygen. This guy is pulling on these electrons more. So really, if I was going to draw this picture to represent what's really happening in an atom, right? I've got some electrons that are making the bonds, and the electrons are moving around. They're always in motion. How are they moving? I don't know how they're moving. But I do know that if I took a bunch of pictures over time, they're spending a lot more time around oxygen than they are around hydrogen. Why? Because they can get closer to a +6, which makes them happy, than they can to this -1, right? So what that means is that over time, this end of the molecule becomes, oops, I'm throwing a term out here. This end of the molecule becomes partly negative. This end of the molecule becomes partly positive, right? The water's a polar molecule, right? But the thing that describes this bond right here and the sharing of electrons is electronegativity, all right? Electronegativity. So let me go back to that periodic trend. Electronegativity are numbers that are measured. People didn't just make these numbers up. They measured electronegativity values, all right? And all right, there's basically trends in electronegativity. It's kind of hard to see that trend there. So let me give you essentially a sketch of the periodic table. So if we had a periodic table, right, and again, we're talking about electrons. Which atom on the periodic table wants electrons the most? Do you remember? Said it a couple times. There's one atom on the periodic table that, given a chance, it will take an electron from anything else. It really wants electrons.
Fluorine.
Fluorine. All right, F. This guy really, 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 really wants electrons. Why does he want electrons? Because he's small, he's got a big charge, and he's got one opening, right? Lots of reasons why fluorine likes electrons. So fluorine is assigned an electronegativity value of 4. And then what scientists have done is they've compared bonds between fluorine and a whole bunch of other atoms, and they've figured out when you bond 2 atoms together, right, like fluorine and hydrogen, they compare how much of this electron density is on the fluorine and how much of it is on the hydrogen, right? And they've come up with a scheme. It's called electronegativity, right? What you need to know about electronegativity is you can find it on a table, right? You can look it up. So if I were to just go to Safari and just do a quick search, electronegativity, pick this guy. It's just a table. Come on, please show it to me and don't give me garbage. Oh, sorry. Let me pick this. Maybe I can get this guy. Ugh. Oh, all right, there we go. It's not going to give me the numbers, is it? Can I look at this one? Please show me this one. All right, there we go. Okay. These are electronegativity values. They're measured, all right? And what you'll notice, I don't know if my pen's going to let me draw on this or not. It's not going to let me draw on this. So let me just do this. Let me put it in Notability. Let me add it to this. Import done. I have no idea where I just added it. Did you see where I added this? Periodic trends, did I put it in there? My wife is telling me it's time to wrap it up. Oh, I don't know what I did with it. Anyways, you'll notice that the electronegativity of fluorine is assigned a value of 4. And you'll see that as you go backwards, the electronegativity values aren't as large, right? And as you go down, the electronegativity values aren't as large. So once again, electronegativity looks just like the size. As the atoms get bigger, they don't hold on to electrons as tightly. As the atoms get smaller, they hold on to electrons more tightly. And so this table, this electronegativity value table, is going to tell you about how much an atom in a bond wants electron density. And we're going to make use of that later to talk about this thing like polarity. Why is water a polar molecule? Well, because oxygen likes these shared electrons more than hydrogen. That's electronegativity. And so the trends are pretty much this. Increasing electronegativity, oh my gosh, I can't write. Electronegativity, which we'll just abbreviate with an EN. Electronegativity increases as you go to the right, and electronegativity decreases as you go down. Again, why is that? Atoms get big as you go down, atoms get small as you go to the right. So this atom has the largest electronegativity, and of course this atom down here, francium, has the smallest electronegativity. And the generic trends are spelled out through that table. And I see that I've gone like way long. Oh my gosh. Are y'all still there? 29 of you hung around. Okay. Any questions before I let you wander off? I will post some practice things that pertain to the next exam. And then you'll have between now and Tuesday to work. Well, you'll have between now and the exam to work on them with the questions, but we'll spend Tuesday answering your questions about things that will be on the next exam. So I'll try to get that posted tonight or first thing in the morning. Okay?
So you're going to post this to this video, right? As well.
Absolutely. I will post tonight's video as well. Did you get the link for yesterday's one through?
Yeah, I got it.
Okay. Will this topic be on the exam? Yes. This topic, periodic trends, will be on the exam. but shapes of molecules and polarity of molecules will not. So up until what we covered today, periodic trends will be on the exam. Yes. Okay.
Is the exam next Thursday?
It is. Okay. April 30th will be exam number 3. Okay. I see a yes from Sammy.
Yep, got it.
All right, guys, it's been awesome. And remember, if you have questions, just send me an email, and I'll see you on Tuesday.
See ya. Good night.
Bye, guys.
Thank you.